Now that we have some motivation, we're finally ready to get to the actual axioms of set theory. So in the first video, we discussed the question, why are sets? And we're hoping to now get to the question, what are sets? Somewhat surprisingly, though, we're not actually going to define what a set is. In fact, there's three things that are going to just be left mysterious in this case. And that is sets themselves, we're not going to define. We're not going to define what membership means. So we're not going to define what it means to belong to a set. And we're not going to define elements. Some of you might be quite confused about the fact that we're not defining these things. These seems like the most essential ingredients to the entire theory. So why wouldn't I do such a thing? Well, let's think about when you have a dictionary and you look up a word. Well, the definition of that word has other words in it. So technically, if you're starting from scratch, you would then have to go and look up the definitions of all of those words. And then you would need to look up the words and the definitions of those words, and so on and so forth, until you're running in endless cycles of definition. So you're trying to pull yourself up by your own bootstraps. What we have to do then is just accept some words on faith that those are things. So what we're going to do is just accept that there are sets, there's membership, there's elements. We're not going to say what those things actually are, but we're going to describe how they behave. Personally, I feel like this is kind of like a watered-down Western version of Zen or something. How we can't talk about the true nature of these objects, but we can only describe the way in which they act. And that's what the axioms are for. And of course, you're still welcome to use your comfortable notion, at least for the beginning of this course, of sets as some collection of objects, like some bag of apples or something. But of course, we're going to find later on that your intuition, it starts to really fall by the wayside when it comes up against the axioms, particularly in the infinite case. So without further ado, the first axiom is the Axiom of Existence. In order to start this theory off, we need to suppose that some set does actually exist. More than that, we're going to assume the existence of one particular set, and that is what's called the empty set. So with our curly braces notation, this is just two braces with nothing inside. This is often denoted as a 0 with a slash through it. One might wonder, well, why the empty set? I think on some level it is intuitively clear that we would want the empty set because it's the most basic thing, right? The whole idea of axiomatically framing mathematics is we want to make the least amount of assumptions and build what we can off of that. So we start with the empty set, and in fact, we're going to be able to show later on that even if we had chosen some different particular set to exist, with a combination of the other axioms, you can derive the empty set anyways to show that this really is these minimal assumption. Okay, so we have the existence of one set, and that's about all our theory has at this point in time. The second thing that we want is what's called the Axiom of Extensionality. This axiom is going to do two things for us. One, it's going to define what we mean by equality of sets. And of course, given your intuition from naive set theory, what this should mean, equality, should mean that two sets have all the same members, right? So equality, we're going to define equality of sets to mean that if X is an element of big X, then little x is an element of big Y, and if little y is an element of big Y, then little y is an element of x. So this is just the obvious, if you will, definition of what it should mean for two sets to be equal. And the other thing is, having this definition in place, that's going to allow you to prove uniqueness of sets. So, for instance, you can now take this axiom and combine this with the axiom of existence to show that there's a unique set with no elements. So really, we're justified in calling this the empty set. So our theory still isn't very powerful. We're two axioms in, and all we have is that there is an empty set. There is a set called the empty set, and it's unique in that property. So moving on to axiom 3, this is called the Axiom of Comprehension. It's this axiom which is going to do away with our set of all sets problem. So what the Axiom of Comprehension says, or what I should really call this, is the axiom schema. Why I say schema is because this is secretly an infinitude of axioms all rolled up into one. So this says that given any set A, and let's say we have some property, so I'll just write that PPTY, some property P of X. So this is some property we can assign to set. So maybe this could be simply the property X equals X, or maybe it's the property X does not belong to X. Clearly this is one pertinent to our situation. So given that these two things, that we have two of these things, the axiom of comprehension tells us that we can build a new set, and this new set is going to be all of those elements of A such that the property P of X holds for that element. Perhaps I should have mentioned this earlier, but when we're doing axiomatic set theory, elements are sets themselves. So absolutely everything we're dealing with in this theory is sets. As I mentioned in the first video, even, of course, there's the set of natural numbers, but then the very natural numbers inside the sets in this framework are going to be sets themselves. So members are sets, everything is sets. Another way to spin this rule around is that, in a certain sense, it's telling us that all our sets look like this form. So in our set of all sets example, we had something that was of the form X, such that X does not belong to X. So in a certain sense, the axiom of comprehension is telling us that we can't just have something bare bones like this in the first coordinate referring to all sets. These elements should be able to be framed as belonging to some other already existing set as dictated by the other axioms. And towards this end, well, let's just take a look. How this actually prevents us from having a set of all sets is a little bit subtle. So what happens here is basically a proof by contradiction that the set of all sets cannot exist. So suppose that we did have V, which was a set of all sets. Now the axiom schema of comprehension tells us that we can now form the set X in V such that X does not belong to X. So, you might be wondering, given the last episode, we saw that this set has problems. This set is contradictory. And that would spell disaster for our theory of sets. So what am I talking about? Didn't I just tell you that the axiom of comprehension is supposed to prevent this from happening? Well, yes, it does. So based on last video, we reasoned that the very existence of this set is contradictory. Therefore, we lead to a contradiction. What's saving us, though, is that we first supposed that a set of all sets existed. We didn't just magically conjure it up naively. So what's going on here is we have an if-then statement. So if the set of all sets exists, then the set of all sets which do not contain themselves exist, and this is a contradiction. So the reason why we don't have this actual statement coming up as a truth in our theory is because this follows from our hypothesis. So we've only hypothesized, we've only assumed a set of all sets to exist, and we saw that then there leads to a contradiction. So therefore, a set of all sets cannot exist, and there's no contradiction in assuming that a set of all sets does not exist. I know that one's perhaps a little bit of a head scratcher, so ponder on it a little bit. But this is how the axiom schema of comprehension saves us. Okay, our theory so far still isn't really that powerful. Our first axiom told us that there is a set that exists, the empty set. The second axiom told us that it's unique. And the third axiom didn't even let us construct other kinds of sets. It simply told us that a set of all sets can't exist in the first place. Finally, at axiom 4, we come to the first axiom, which is going to actually allow us to construct other kinds of sets, and that is the axiom of pair. What this says is that if we know two sets to already exist, say a set A and B, then we can form a new set which simply contains those two sets themselves. And now we actually get a proliferation. Suddenly we've gone from a single set, now we can construct infinitely many sets. So for example, to start off, the first thing that we only know to exist is the empty set. So we can consider the empty set for our first set and the empty set for our second set B. And now this allows us to form the second set, which is the set containing the empty set and the empty set. Now, by the axiom of extensionality, we can see that this is actually just the set containing the empty set, because all the elements of this set belong to the set on the right, and all the elements of the set on the right belong to the set on the left. In general, we can see then that our normal intuition from naive set theory, being that there's only one of each kind of element in a set, does actually hold here. So we can reduce it down to the single case. Now we can come up with a few more interesting examples. I can take the empty set and pair it with the empty set, the set containing the empty set. And if I were to apply the axiom of pair to this, I now get the set containing the empty set and the set containing the empty set. So we could keep going. But there's going to be an explosion of curly braces and empty sets. And you can see how this is all expanding now. So now you could pair the empty set with this new set we've made, or you could pair the set containing the empty set with this new set we've made, or this newest set could be paired with itself, or this set could be paired with itself, and all those could be paired with each other, and it just goes on and on and on. So now we've got infinitely many sets, which are kind of just stacked up layers of emptiness. before we find ourselves knee-deep in some nihilist philosophy that the bottom of that everything is simply constructed out of nothingness, let's move on to the fifth axiom, which is the Axiom of Union. Now, this isn't actually what you might expect right away, just defining a union of two sets. What it says is that if we have some set, for any set that we already have in our universe of sets, we can form a new set, U, where an element is going to belong to U if and only if that element belongs to some A and that A belongs to the set S. A notation that we sometimes use for this set U is this cup, so it's just like the cup shape that you use for a normal naive union of two sets, and we just put it in front of the set S. So this is really an operation that is defined only for a single set. So let's take a look at how this actually works, and we can use one of the sets we've constructed in our universe from the previous example. So let's look at what it does to the union of the set containing the empty set and the set containing the empty set. So what the axiom says is that we can only grab those elements which are elements of the original set. So first, let's find these middlemen here. So we have A corresponding to the empty set. Well, there's nothing in A in this case. So there's absolutely nothing for us to toss into our set, which is the union. But the other case is when A is the set containing the empty set, in which case it has exactly one element, that namely being the empty set itself. And that exhausts all our possibilities, so we see that this single union of this set is just the set containing the empty set. You might be thinking, well, what's going on? Why are we calling this the axiom of union? It's really cutting a set down. If anything, there's really no uniting of sets going on, and don't we want to be able to retrieve our original naive notions of set theory, such as union and intersection? And yes, but the axiom of union together with the axiom of pair actually gives us this. What we can do then is define A union B. We simply define this to be the set which is the union of the set containing A and B. So we're able to construct this because the axiom of pair says that if you have two sets A and B, then you're allowed to construct the set containing both of those sets. And now our axiom of union tells us that we can always take the union of any singular set. I'll leave it to you to check that this definition of union actually agrees with our standard definition of union just by writing out some naive examples of sets. So now our theory is getting kind of robust. We can form a whole bunch of different sets, and some of them are unions. We have union, we have axiom of pairing, and even though a lot of these sets are just the empty set stacked inside a bunch of braces, we're going to see that this can really recover for us under the right interpretation a lot of mathematical structures you already care about. There's one more axiom that we want in our sort of beginning canon. There's a lot more belonging to ZFC, but the first 6 axioms we're going to get a lot of mileage out of first before exploring some of those other topics. But before I tell you about this last one, we need to make a quick definition. And that is a subset. So we're going to say that a subset S of a set A is any set which obeys the following property, that is, if X is in the set S, then X is in the set A. Again, this is just our normal intuitive idea of what a subset should be. It's some sub-collection, right? So anything that belongs in S, which is possibly smaller than A, must belong to A itself. And this brings us to our sixth axiom, which is the Axiom of Powerset. Again, this is going to line up directly with our intuition, unlike, say, the Axiom of Union. It's in its original carnation. And what this tells us is that given that we know some set S to already exist, then we can form a set script P of S, which we call, obviously, the power set. And the defining feature of the power set is, of course, any element of the power set of S must be a subset of S. And furthermore, if anything is the subset of S, then it is going to be in P. In other words, the power set of S is defined to be the set of all subsets of S. So that concludes the axioms that we need to start off with. We have the Axiom of Existence, says that an empty set exists. We have the Axiom of Equality or Extensionality, telling us that, giving us uniqueness and telling us what that even means. The Axiom of Comprehension, which restricts what kind of sets we can actually have. The Axiom of Pair and the Axiom of Union, which actually allow us to construct different sets altogether. And finally, our sixth axiom, the Axiom of Powerset. So with all these in mind, we'll be on our way to the next video. Comments, questions, concerns, you can leave them in the comments below. And thanks for watching.